What mechanisms contribute to capacity attenuation observed in these materials over multiple cycles? How does the initial specific capacity compare to the capacity retained after several cycles, and what factors drive this decline? Why does capacity fade become more pronounced with an increasing number of cycles, and what structural or chemical changes are responsible? How do the charge-discharge curves illustrate the relationship between sodium-ion intercalation and deintercalation processes? Can Davis-Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What role do voltage plateaus play in understanding the phase transitions occurring within P3, O3, and O3? How does the presence of multiple voltage platforms indicate severe phase transitions, and why is this detrimental to cycling performance? What are the specific phase transition mechanisms occurring in these materials during charge and discharge cycles? How do these transitions affect sodium-ion diffusion and overall battery efficiency? What structural characteristics of P3, O3, and O3 contribute to the observed voltage platforms? How does the evolution of the crystal structure during cycling impact its stability and specific capacity retention? In what ways does the interaction between sodium ions and transition metal oxide layers influence the electrochemical behavior of these materials? Are there external factors such as temperature, pressure, or electrolyte composition that accelerate phase transitions and further degrade cycle life? What strategies have been proposed to mitigate the negative impact of phase transitions in P3, O3, and O3? Could material modifications or doping approaches improve their cycling stability while maintaining favorable electrochemical properties? How do these materials compare to other sodium-ion cathode materials in terms of phase transition severity and capacity retention? Are there alternative synthesis techniques that could enhance the structural integrity of P3, O3, and O3 while reducing phase-related degradation? What role do defects or vacancies within the crystal lattice play in the capacity fading of these materials? Can electrolyte optimization or structural engineering extend the operational lifespan of sodium-ion batteries using P3, O3, and O3? How do advanced characterization techniques such as X-ray diffraction or electron microscopy help in understanding the structural evolution of these materials? What lessons can be learned from other transition metal oxides regarding phase transitions and cycle performance improvements? Are there emerging research directions that focus on overcoming the inherent limitations of P3, O3, and O3 for practical sodium-ion battery applications? How does the potential range of phase transition influence the electrochemical behavior and stability of these materials? What?